Hello and welcome to this video lesson. In this video, we will be looking at some practice question in the electricity unit, and the focus is circuits. In the first question, we got two conductive spheres over here, and we know they're conductive because there is negative charges all around it. And in a conductor, the negative charges are not attached to the atoms, and they actually get spread out around the surface. So we get two of them. And initially, they're just, one of them is negatively charged, one is positively charged because we don't see as many negative charges in here. And then we connect the wire, and we want to see how the charges travel or what happened to the charges afterwards. So starting off, we have to write down the charge equation before the wire was connected. So I'm going to go ahead and write this as positive 5. I'm writing positive 5 because we have 1, 2, 3, 4, 5 positive charges. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 negative charges. So this is going to be plus negative 11, and that's going to give us negative 6, and that's for A. And for B, we have 5 positive charges, and we can count 1, 2, 3, 4, 5, and we have 1, 2, 3 negative charges, so plus negative 3, which is going to give us positive 2, and those are the net charges initially before we connect the wire. After connecting the wires, things are going to happen. So complete the drawing for the charge diagram after the wire is connected and write down the charge equation. So what's going to happen after we connect the wire, we're going to see that the charges from here, the negative 6, these ones are very unhappy here. So they're going to start moving. And the charge over here first is going to start going through the wire. And as soon as it goes through the wire, one of the charges here, the negative charges, because there's infinite number of electrons here, is going to start moving in this direction. So one of the charges, or one group of charges, is going to move, another group is going to go here, and it's going to get stuck to these ones. So initially we have at least negative 3 charges. So let me draw those using, I'll draw them using red. So we have 1, 2, 3. Actually, I'll draw the original ones with black. And then we've moved 1, and 1 kind of leaves. And then now our charge becomes negative 5 and 2. So I'm going to write those down on the side here. It kind of helps me keep track of what's happening. So we got negative 6 and positive 2. I moved 1 charge, so it becomes negative 5 and negative 1 because I'm adding a negative charge. So negative 2 plus negative 1 becomes negative 1. Then I move another charge, let's say this one, and it's going to go through the wire, and 1 unit of charge is going to push all the electrons here, and another one is going to go here, and I'm going to add 1 here, and now I'm going to have negative 4 and 0. So it is now neutral. So I can just leave it as 0 instead of positive or negative 0. It's still unhappy here. There's still a net charge of negative 4. So another electron is going to go through the wire, or another group of electron is going to go. And then we're going to have negative 3, negative 1. And I'm going to just add 1 group of electrons there. It's still unhappy because we got negative 3 here and negative 1 here. So I'm going to have to move another group of electron through the wire. So now I'm going to have another set of electron. Again, I'm not drawing them on the atoms. I'm drawing them outside because they don't actually like being close to each other, so they go around the surface in a conductor. And by moving this last one, I get negative 2 and negative 2. Now, they're still unhappy because there's a net charge here, but they're equally unhappy. So there's negative 2 here and negative 2 here. And this is our last diagram. So basically, we have negative 2 charges on both. So I'm going to add these in. It is now neutral. I'm going to add 2 electrons, and I have negative 2 and negative 2. And it is complete after all of the electrons are transferred, after we have equal net charge between the two. So to write the final net charge equation for both, for A, I'm going to use pink. I'm going to have positive 5 charges, and I have negative 7, which is equal to negative 2 net charge. And for B, you can see we have the exact same thing because electrons are no longer moving. And we get negative 2 and negative 2. So now in this question, we've answered A. Write down the charge equation. So we have that over here, usually 1 mark per each. So we got 1 and 1. And then drawing of the electrons afterwards. These are complete. And we got these ones over here, the charge equations after. In the next question, we got a battery of potential difference or voltage of 9 volt with a resistor of 2 ohm that is connected in series, and a 3 amp fuse is connected to the circuit for safety, and we want to determine if the fuse burns out or not. And to do this, basically the idea is if we connect a fuse into a circuit, if it has a rating of 3 amps, or basically anything, in this case 3 amps, if the current that's going through the wire is anything larger than that, it will burn the fuse. It will then open the circuit, and it will not allow any current to flow through, and that will protect our components from burning, because too much current can actually damage the different components. So to test this, we know that the battery is 9 volts and the resistor is 2 ohms. So the total current going through our resistor here, or through the wire, is going to equal to, I'm just going to say I battery is going to equal to the voltage across the battery divided by the resistor. There's only one resistor, so it's going to be resistance here. The voltage is 9 volts, and the resistance is 2 ohms. And when we divide this, we are going to get 4.5. And our unit here is amps. And we can see that the current that's going across the battery or across the whole circuit is larger than, actually, the way I'm going to write this, I'm going to write that 4.5 amps is larger than 3 amps, and this is just the fuse. This is what the fuse allows. This is what the circuit has. And therefore, because it's larger, the fuse is going to burn out. So I'll write that down. And what we have to do in this type of situation, because we are passing too much current through our circuit, is to add a resistor of some sort in order to kind of allow it to have less current going through it. Or in this case, we don't even talk about the components. We need a component. The component itself is going to have some resistance, and hopefully that will reduce the current enough so that the fuse will not burn. But in this case, all we have to do is calculate the current and compare that with the current going across the fuse. If our current is larger, it will burn the fuse. If it's smaller, it's safe, and it will not burn the fuse. All right, in the next question, we want to sketch the potential difference graph for loops A and B. So we have a circuit. This is a mixed circuit. It has a lot of resistors. We have one resistor here connected with that in parallel. We have two other, B and C, that are connected. And we want to see how the voltage is changing across the two loops. So when a unit of electrons starts moving from here, they get a certain amount of potential difference here, or a certain amount of energy, and this is 10 volts, meaning 10 joules per unit of charge. So they're going to collect about 10 joules of energy, and they're going to go here. And at this junction over here, they're either going to go straight or they're going to go down. The group that goes down here, they go through loop A. So they're going to go here, they're going to go through resistor A, and then they're going to come back and they're going to come here and they're going to go and get energy again. So they gain this much energy, they're going to lose the same amount of energy. So for loop A, a group of electron that comes here, basically at point 1, that's going to be our reference point. We're going to say that they have 0 energy there. And when they go across the battery, they're going to gain energy. So they're going to gain approximately 10 joules of energy. You're not always asked to write these numbers, but here, because we have the numbers, I'm just going to write that this is 10 volts. And they're going to go through, and you can actually, you don't even have to write it here. If you want, you can write the values here. This is 10. And then it's going to go. It's going to go, they're going to go, they still have 10 joules of energy, still have 10 joules of energy, still have 10 joules of energy. They get pushed in this path, so they go here, and at stage 3, they still have 10 joules of energy. So in the wire, since we're assuming an ideal wire here, there's no loss in energy. So between 2 to 3, we still have 10. And then they go through the resistor here, and they're going to lose all their energy because there's no other resistors along the way. So they're going to lose all of that 10, and they're going to have 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way to 1. So they're going to lose all of their energy by state 4, or approximately around 4, and then they're going to have 0 energy. And this is our potential difference graph for loop A. For loop B, let's take a different set of electrons. They are going to come here at 0 energy, and they're going to come and they're going to gain 10 joules of energy. They're going to move up to here, and I can even start drawing it here. So at state 1, we're going to assume that electrons have just no energy, and by state 2, they have gained 10 joules of energy. So I'm going to go here, and I'm going to just write 10 volts here, because that's how much each group of electron, that's how much energy that group of charge has. And they're going to go and they're going to be pushed in this direction. So from 2 to 5, they're just going to have that same amount of energy. They have not lost any energy because it's an ideal wire. So we still have 10 volts here. And I'll just put the volt signs here as well. And then they're going to go through B. We don't know how much is lost here, and we don't have that information at the moment, so let's just continue and see what's going to happen. We know that it's going to lose certain amount of energy, up to 6, and then they're going to carry whatever energy that is left. They're going to keep going, they're going to keep going, and then they're going to lose another set of energy here. That amount of energy is given to us, and that's 4. So I'm just going to write that here. Delta VC is equal to 4 volts. And they're going to lose 4 joules of energy, that group of charge. It's going to move. They're going to move all the way back to this point, and they're going to have 0 energy here. So we know that at this point they have 10 joules of energy for the amount of charge. Here they have 4 joules of energy because we know they're going to lose all of that energy. So we know that between stage 7 to 8, they're going to lose the amount that they're going to lose is 4. So between 7 to 8, they are going to lose about 4. So 4 is somewhere here. So I'm going to just write 4 volts here. And I know that between 6 and 7, this is kind of like solving a puzzle. 6 to 7, they don't lose anything. They're going through a wire. There's no resistor here, so they just carry their energy during that point. So between 6 and 7, there's no loss in energy. And then the rest has to be spent between 5 to 6. So we know that they gain 10 joules of energy. They're going to lose 4 joules of energy, so they have to lose 6 joules of energy here as well. We don't even write that value down, but we can just go down. We know that that's the difference of 6 and we have 4 volts in that section. And I'm going to try to draw this as well. Between 8 to 1, they're just going to carry 0 joules of energy. So once again, for this group of a charge or electrons, they're coming in at state 1. They have 0 joules of energy. This is again reference. They gain 10. They move. They still have 10. They still have 10. They still have 10. They still have 10. They don't move in this direction. They're just pushed through. So they have 10 joules, 10 joules, 10 joules. And at this point, once they go through B, they're going to lose about 6. And right here, they're going to have 4. They're going to carry 4, 4, 4, 4, 4 through the wire. They don't lose any energy within the wire. Again, the ideal wire condition here. And then from here to here at resistor C, they're going to lose 4. That's given to us over here. And they're going to have 0, 0, 0, 0. They're going to keep getting pushed. They're going to keep getting pushed. They can't go in this direction because there's other charges moving in this direction, and they can't actually move in that direction. So they're going to keep going with 0 joules of energy, and they're going to gain some energy again. So this is how we draw the potential difference graphs. We just look at a group of electrons, where they move and how much energy they lose. So they always gain energy when they go through a battery or any source, and they lose energy when they go through any types of loads such as resistors, lamps, or other components. In this question, we are asked to determine the equivalent resistance between points C and D. In this particular case, from point C to D, there are 3 resistors, and they're all connected in series. We know they're connected in series because there is basically no junctions. So an electron that's moving here, they have to go through A, they have to go through B, and they have to go through A again. There's no other way for them to transfer, so this cannot be a parallel circuit. So because we know they're connected in series, the resistance equivalent is going to equal to RA plus RB plus RA. This is because they're connected in series, and I'm just going to write it out. And the rest is just plugging in the values. So RA is 1 ohm, RB is, and for equivalent resistance, I'm okay if you don't write the units. You can just write the final unit at the end. 1 plus 2 plus 1 again, because RA is 1. And you can just, again, if you want, you can just write it as 1 plus 2 plus 1 for short. And that's going to be 4 ohms. So the final equivalent resistance here is going to be 4 ohms, and I'm going to just box my answer. That is my final results here. The steps I want to see for this types of question or this type of question is, especially when they're in series, you just say that they are in series, and this is the equation we're going to use. And I want one step showing all the values plugged in and the final answer. So you can skip this one if you want, but I do want the final answer written as therefore the equivalent resistance is equal to 4 ohms, and make sure you always show your unit for the final answer. In this question, we are asked to determine the equivalent resistance, again, between points C and D. So electrons that are going to go through between points C and D, they actually split. We can't have charges moving through just one path. Some of the charges are going to go through A, some of them are going to go through B, some of them are going to go through B again. We know that RB is larger than RA, so most of the electrons will actually choose the path of least resistance and go through A. Some will go through B, some will go through this other B. Probably similar number of electrons are going through here, but more are going through here. But we're not even asked for the electrons, so we're only asked for the equivalent resistance. Because the electrons are splitting between these paths, these 3 paths are actually connected in parallel. But within each wire, so when electrons, if they go through this path, they only going through one resistor, so we don't have to add anything in series here. Electrons that are going through this path are only going through this. We don't have to add anything in series here. And electrons that are going through this path are only going through this resistor, so we don't have to add anything. So this is a pure parallel circuit or a parallel path, and it's not a mixed circuit. So since I know that the equivalent resistance here, since I know that it's a parallel circuit, I'm just going to write that the equivalent resistance, 1 over R equivalent, is equal to 1 over RA plus 1 over RB plus 1 over RB. Because there's 3 of them, and in a parallel circuit, the equivalent resistance 1 over R is going to equal to 1 over R1, R2, 1 over R1 plus 1 over R2 plus 1 over R3 plus ... all the way to however many resistors you have. So I'm just going to write here that I'm using this equation because they are in parallel, and that's all I need to really show. Then I'm going to go ahead and solve, and equivalent resistance here is going to equal to 1 over RA is 1, 1 over RB, RB here is 2, 1 over RB again, this is 1 over 2, and let's solve this. There's many different ways of doing this. You can basically say 1 over 2 plus 1 over 2 is 1, 1 plus 1 is 2, or you can get a common denominator of 2 like this, and then write that 1 over REQ is equal to 4 over 2. Or you can say that simplified it's equal to 2 over 1 or just 2. The important thing, it doesn't really matter how you get to this point. Some of you folks are able to just go from here to here in one step, and that's completely okay. I'm happy if you do that. But at this point, what a lot of students tend to miss is the fact that you didn't just calculate REQ, you calculated 1 over REQ. And in order to actually get REQ, or the equivalent resistance, you need to take the reciprocal. In order to take the reciprocal, you switch these two and you switch these two, and then you have R equivalent over 1 is equal to 1 over 2, and that just means that R equivalent is equal to 1 over 2 ohms. And you can leave it like this, or you can write this as 0.5 ohms. Both answers are acceptable, but this is the final answer. So in this question, some of the steps that I want you to always show is the first step here, showing kind of the idea that this is the equation and this is because they're parallel, and then one showing all of the values plugged in. And then this step is unnecessary. You can actually show it if you want. I know that some of you folks at this point are strong enough in math that you can go from here to here, or sorry, from here to here in a very short time. So I'm just going to put a check mark here. I want to see this, and I want to see the final solution. So at that point, once you have this, you can take the reciprocal. You don't have to show this. This is fine. We are now asked to determine the equivalent resistance between points C and D. We have two types of resistor, A and B, and we have a mixed circuit here. The reason why it's mixed is because when electrons are moving from point C to D, they have to choose a path, and here this makes it parallel. But within this parallel circuit, when they go through this wire, there's actually two resistors and not just one. And since there are two resistors here and they're connected in series, we have a mix of series and parallel circuit, which makes this a mixed circuit. Now, the way we can analyze this is whenever you see that you have two different junctions, I usually personally like to point them out. So there's a junction here and there's a junction here, and the wires between these two junctions are connected in parallel. anything between those 2 points along the same wire is always connected in series. So I'm just going to draw a little dash section over here. And these are connected in series. I'm going to call them RAA. And once I have RAA, this one big resistor, then this RAA and RB are connected in parallel because this is going through one wire and getting to this junction, and this is going through another completely separate wire and going through the same junction. So once again, if you see them going through the same wire, just connect them in series, nice and fast. And if you see them connected between two different wires along the two different if you look at the two junctions and you see two separate wires connected, that would mean that they're in parallel. So first I'm going to calculate RAA here. And RAA is going to equal to RA plus RA, two RAs. And this is in series because they're on the same wire. As long as they're in the same wire, it means that electrons cannot split. They have to go through both, so it is in series. The values here for RA are 1 plus 1, which makes this 2 ohms. Now, for the equivalent resistance, I have to add RAA and RB in parallel because, again, they are connected between two wires, and we have a junction here. If they were on the same wire, we would connect them in series, or we would calculate the equivalent resistance in series, but here they are on separate wires. So the 1 over R equivalent is going to equal to 1 over RAA, that's this one over here, and since that is connected in parallel with RB, it's going to be 1 over RB. And this is because they are now in parallel. And since I have a parallel and series, this is a mixed circuit, or mixed connection. So 1 over REQ, when I write RAA, I don't have to write it in every step because they're pretty much the same. RAA is always the same. Whenever I have 1 over REQ, I often just write it in every line because it's a little bit easier to kind of connect it at the very end. 1 over RAA, I calculated that to be 1 over 2. RB is also has a value of 2. So I'm just going to put 1 over 2. And I get 1 over REQ is equal to 1 over 2 plus 1 over 2, which is 2 over 2. I'll just write it out. And then at this point over here, I can simplify this, or I can take the reciprocal. It's up to you which way you want to do it. I'll take the reciprocal here, and I'll say that REQ over 1 is equal to 2 over 2. So REQ, or the equivalent resistance, is equal to 1 ohm. Because 2 over 2 is equal to 1, and REQ over anything over 1 is just itself. So I will get equivalent resistance here is equal to 1 ohm, and I'll put a therefore statement, and I will highlight I will box my answer, and that's something I want you folks to do as well. So the steps I want to see in this one are the fact that we have a series here, so I'm going to point that out, and I kind of added them. So RAA refers to two resistors A and A. If one was A and one was B, I would write it as AB. If one was A and one was C, I would write it as AC. 1 plus 1, I want the numbers plugged in, and I want the final solution in there. The value, I want this step saying that these are in parallel. I want the numbers plugged in. And the other steps are really for you, and you don't really have to show them. I would suggest that you show a few steps in case you make a boo-boo, and if you make a boo-boo, you might get some part marks along the way. So once again, I want every time you do these types of questions, I want the equation saying why you chose that equation. Plug in the values. Do not forget to take the reciprocal, and that's your final answer at the end. So sometimes it's also good to, yeah, sometimes depending on the situation, you might get a mark for taking the reciprocal as well, but that's more math than it is science. So I'm mostly looking for the final solution there and some part mark along the way. In the next question, we're asked to determine the missing values and determine the power of the speaker. So we have a circuit here, and in this circuit we have a battery, we have a speaker, we have two resistors here. One is 10 ohms and the other one is 6 ohms, and the resistance by the speaker is also 4 ohms here. A battery, 4 volts. We are asked to find the current across the battery, the equivalent resistance across the circuit. We are asked to find the current across the speaker, the potential difference across the speaker, current across resistor B, potential difference across B, current across C, and potential difference across C. So looking at the circuit, first of all, we can see that if the group of electrons were to move from the negative terminal to the positive terminal, they will go, they will go, they will go. They are not splitting anywhere. They're still going through the same wire, same wire, same wire, same wire, same wire, all the way, meaning that this is a circuit that is connected in series, and we don't have to worry about anything in terms of it being a parallel circuit or a mixed circuit. So that makes it a little bit easier. Then what I usually do in these types of questions, I look for information. So I look to see if there is any set of 2 information given for the same component. And if that's the case, I can always use, I'll write down our equations here. So V is equal to IR, that's delta V, and we have power is equal to I delta V. We also have equivalent resistance for a series circuit, which is R1 plus R2 plus dot dot dot. This is in series. And we have we have 1 over equivalent resistance for a parallel circuit as 1 over R1 plus 1 over R2, and this is given, this is parallel. So in this situation, we don't really need to care about this. We only have to worry about the equivalent resistance here, possibly. There's one other equation that I don't often write, and that's equivalent resistance can also be calculated through the potential difference across the battery over the current across the battery. So that's another equation. I often don't write it down. It's something that you can derive from this equation over here, but it's also there. So if I have any 2 pieces of information on the same component, I can find a third one. If I had R and if I had voltage, I could find current here based on this equation. If I had power and if I had current, I could find voltage. So that's the first thing I look at. Do I have 2 pieces of information on any of these? And I don't. I have the potential difference here, and that's the only one I have. I only have the resistance here. I only have the resistance here, and I only have the resistance here. If that's the case, I cannot use this equation at the moment to find any other information for the components. And when that happens, usually then I go to the equivalent resistance and figure out if I can find out what the equivalent resistance is. There are 2 different ways of finding the equivalent resistance. Once again, one of them is dividing the potential difference across the battery by the current across the battery. And I don't have the current across the battery, so I can't use the easy way of getting there. The next way is using one of these 2 equations or a mixture of the 2. At the moment, I can see that these resistors are connected in series. So I can go ahead and say that the equivalent resistance is going to equal to RA plus RB plus RC. And this is because they're connected in series. I have all of those values. I have RA as 4, I have RB as 10, and I have RC as 6. This adds up to 20 ohms, and this will give me the equivalent resistance. And that's one of the things I'm looking for. So I'll write therefore Req is equal to 20 volts, and that's one of my final answers that I'm going to highlight and box. Now that I have the REQ, I'm going to put a check mark on it, and I'll write it down. I'll write it around here because they're really they're connected. REQ is equal to 20 ohms. And now I have two pieces of information for one of my components. And again, equivalent resistance doesn't mean the resistance along the battery. It means the resistance across the circuit. But that does help me figure out what is the current that is passing through the battery. And I can find that through this equation over here. So I have to use the equivalent resistance equation twice here in order to find that information. And I will. I'm going to say that equivalent resistance is equal to delta V1 over I1. At this point, I can rearrange the equation to find I1, or I can write the values in and then rearrange. It doesn't actually matter how you choose to do this. One of the ways is to write 20, that's the equivalent resistance, is equal to delta V1. We have that value, it's 4 over I1. And I'm trying to solve for I1 here, so I'm going to rearrange the equation by either cross multiplying these two, that's the shortcut, or multiplying both sides by I1 and dividing by 20. So I'm going to write my steps here so you have an idea about what's happening. If you're good in math, then this will not be an issue. You can do it in one step. But I'm going to multiply both sides by I1, and I'm going to get 20 I1 is equal to 4. And then I'm going to divide both sides by 20, and I'm going to get I1 is equal to 4 over 20. Now, 4 over 20 is equal to, and usually I ask you to write the units here. For this, let's just write the unit at the very end. Make sure that for all of your answers, you write the final units. 4 over 20 is same as 1 over 5, which is about 0.2 amps. And make sure that you box your final answer. In this case, I1 is 0.2 amps. And again, you could have done it this way. You could have right away rearranged this equation and said that I1, I'm going to cross multiply here. I1 is equal to delta V1 over Req, and then plug the values in as 4 over 20. So the steps that I'm looking for here, let's go back and make sure that we have these. So I want this, I want the equations, I want the final value, I want the equation, I want the values plugged in somewhere. So this step, any of these steps really work, and I want the final answer here. These are the main steps, and if you show middle steps, often you can get part marks if you make a boo-boo. But the main steps that I'm looking for are really these ones. Okay, now I have found I1. It's beautiful. I have a lot of information now. I1 is equal to 0.2 amps. And since I have the 0.2 amps here, I know that this circuit is a circuit that is in series, meaning that electrons are all moving and they're not splitting. They are not changing their path. They're always moving through the same wire, meaning the number of electrons that are moving through this cross section every second are the same as the number that are moving in this cross section, because this is a lineup of electrons and they're all being pushed by the battery. So if one electron here is moving, this one is moving at the same time, this one is moving at the same time, this one is moving at the same time. So therefore, the current here is going to be the same across the whole circuit. So since that's the case, then I know that IA is equal to IB IB, which is equal to IC, which is equal to I1, because all of them are the same, which is equal to 0.2 amps. The reasoning here is that these are in series. So I'm going to box this, and I'm going to highlight this as well. So basically, we just found a lot of information. We just found out that IA here is 0.2, IB is 0.2, and IC is 0.2. Excellent. Now I have two pieces of information for all of my components, and I can go ahead and use my equation delta V is equal to IR. So I'm gonna do it for I'm gonna have to find the by the way, I'm first going to show you that for these types of question, I'm looking for this and the reasoning that this is in series, and in this case basically you're getting it mark usually for understanding that IA, IB, and IC are all the same. That could be about 3 marks. And I'm going to go back and kind of put a check mark beside everything that I found. And all I have left is the potential differences. So I know that potential difference across A is equal to IA R A. And that's just going to equal to 0.2. RA is 4. And this is going to equal to 0.8. I'm going to write my unit at the very end in this case. And delta VA is going to, therefore, delta VA is equal to 0.8 volt. And this is the potential difference across A is going to be 0.8. I'm going to do the exact same thing for all the other components. This one is going to be IB RB. This is 0.2. Resistance B is 10. So this is going to be 2 volts. And therefore, the potential difference across B is equal to 2 volts. And I'm going to do the same thing for C. Potential difference across C is equal to ICRC, which is 0.2 times RC, which is 6, which is going to give me 1.2 volts. And delta VC is equal to 1.2 volts. You can just write your therefore statement on this step. You don't actually have to write it. You don't have to write it. You don't have to write another step. So what I'm looking for in these types of situation is the equations and the final answers. So that's how it's going to look like. I want the numbers plugged in as well. That's definitely something I'm looking for. And that's it. So I'm going to highlight these as well. And now I have found my VA, or potential difference across A, potential difference across B, and potential difference across C. The last thing that I'm asked to do for this question is to find the power across the speaker. The speaker is this one over here that's connected to resistor A. So the power of A is going to equal to the current across A multiplied by the potential difference across A. So I'm just going to do that here. For part B, power across the speaker is going to equal to the current across the resistor multiplied by the potential difference across it. The current was calculated to be 0.2 amps, and I'll write the units on this one. You can just write it as regular values and write the units at the end. The potential difference For A, that's up here. Let's calculate it as 0.8 volts. And when I multiply the two values, I'm going to get 0.16 watts for my final answer. So the power, therefore, power of the speaker is 0.16 watts, and that's my final answer. You can just write power. A is equal to that as well with your therefore statement, and that is good. So what I'm looking for here is this step, numbers and the equations, and that's how you get your power there. Now, for students who are really keen on checking their answer, one thing about these circuits is that the power spent on the components will always equal to the power across the battery, or the source. So the power of the source will equal to the addition of all the powers of the components. So you can always check and say, okay, the power here is I1 times delta V1, that's 0.2 times 4, which will be 0.8 here. So I'm just going to write this again. You're not asked to do this, so I'm just going to write it on the corner so we can kind of check. We found the power across the speaker to be 0.16. I'll write it out. This one over here, the current is 0.2. The voltage was 2, so 0.2 times 2 will give us 0.4. And the power here is 0.2 multiplied by the voltage here, which gives us 0.24. And we can always check and add these up. So 0.24 plus 0.16, you can obviously do this on your calculator, will end up being 0.4, and 0.4 plus 0.4 is 0.8, which is equivalent to the amount of power that is spent from the source. So you can always check your answers based on that logic. All right, for our last question, determine the missing values, determine the power of the speaker and the microphone. Okay, a lot to do for this one. Let's get started. We have the electrons kind of coming in, getting 12 joules of energy, or 1 unit of charge is going to get that much. They're going to move. They're going to split. Some of them are going to go to the speaker, and some of them are going to go through the microphone and a resistor. This is already a mixed circuit because we have both parallel and series components. So let's do something. With this, I'm going to start off and kind of see what information I have, and I'm going to write them beside my circuit. You don't always have to do this. Sometimes you can do it on a table beside it. You can just write all the currents, current, voltage, and resistance for A, B, C, and that way you can kind of see everything. But in this case, I'm going to go ahead. I have IA, so I have the current here, so I'm going to write IA. I have IB, so I'm going to write IB here. I don't have IC, but I know that when when electrons are moving through this path, it's the same wire. The wire isn't changing. So as they move through here, they have to go through here, and they have to go through here. So the push by the battery of all the electrons here will push electrons here, will push electrons here, and will push electrons here. Since they're on the same wire, they're in series. And when things are in series, the current across that wire does not change. So IC is actually equal to IB. I can just write that right away. This is equal to 4 amps, and this is because they are in series. So I have IC, and that is nice. I'm going to put a check mark here, reasoning and getting the value right. And then, okay, so I'm going to put a check mark here as well because now I have that one. I have delta V1. Okay, good. I have, what else do I have? I know RC value is 2, so I also have RC. So I'm going to kind of highlight that in purple because now I have it and I just want to make sure that I kind of know every information that I do have. Okay, perfect. Now that we have this, we can already start calculating a lot of information. Let's start off by our first thing that we usually do. So the first thing we usually do is we look at all of the components and see if there are any for which we have two pieces of information. In this case, for this one, I only have one piece of information, which is the 2 amps at the moment. I don't have anything else. Maybe with logic, I will find some other information as well, but so far the information that's given to me, I only have IA. For this one, I only have IB. For this one, I have two pieces of information. As soon as I have two pieces of information, I can find the third one. That's exactly what I'm going to do. That's how we usually solve the puzzle. So since delta VC is equal to IC multiplied by RC, I know that my IC value is 4. I just saw that above. RC value is given to us as 2, meaning that the potential difference across there is 8 volts. So therefore, the potential difference across C is 8 volts. And I am going to highlight my answer there. In terms of procedure, this check mark, and a final answer. And now I'm going to go ahead and say that I have delta VC here as well. Also put a check mark here. And perfect. Good. All right, we're going to continue to solve this puzzle. I'm going to look to see if there's any other information at the moment, where any other components where I have two pieces of information. Just one, just one, just one. Okay, I can't do anything else at the moment. I have to use my other information or other knowledge of circuits that I have. One of the knowledge pieces that I have is the fact that when electrons are moving and they come through a junction, they split. So at this point, I know that the total amount of current that's passing through this wire, which is I1, is going to come, is going to come, is going to come, is going to come, and it's going to split. Some of it is going to go here, and some of it is going to go here. That's the only path they can take. They cannot go, not all of them are going to go here, not all of them are going to go here. Since that's the case, I know that current going across the battery, I1, is going to equal to, it's going to split at this junction over here. I'm just going to name this, I'm going to just call it junction 1. And I'm going to write at junction 1, I1 is going to split into 2. Some of it is going to go here, some of it is going to go here. The ones that are going to go here, this is going to be IA, and the ones that are going to go here are either IB or IC. It doesn't actually matter. They're the same value. So I'm going to write IA, that's this wire over here, and the rest IB or IC. Again, same value. You just have to write one of them. Just make sure you don't write both. Okay, I have the value of IA that's given to me. That's 2. And I have the value of IB. It is 4, meaning that the current there is 6 amps. And I'm going to highlight this. Here are my check marks. I just want to change color. This one, and this one. Now I have I1 and I have delta V1 as well. That's given to me as 12. And as soon as I have the potential difference across the battery and the current, I can calculate the equivalent resistance. So the equivalent resistance is equal to the potential difference across the battery divided by the current across the battery. And the potential difference is 12 and the current is 2, meaning that the equivalent resistance is 6 ohms. And I'm going to highlight this or box my answer here. And check mark, check mark, and check mark. Already found a lot of information. Let's put some check marks beside things that I did find. So I found R equivalent here. I'm going to put it like this, or purple is fine. Is there anything else? I1. I found I1, which is nice. I found delta VC. Okay, good. Now, let's see if I can find any other information. It seems as though I can use the equivalent resistance and kind of find some information there, but it's a little bit easier way. What I'm going to do next, because I don't have any other components where I have 3 pieces of information for, I also found REQ here. That's already done, and I have all the information for that. The next piece of puzzle that I'm going to find is I'm going to look for the voltage or the potential difference across the different components. And I'm going to start off by following a path of an electron through a loop. When electrons are moving, they can either go here through this loop, or they can go through this loop. There is no other way. If they go through this loop, I'm going to call this loop loop A. Loop A. And within the loop A, when they go through, they're going to gain 12 joules of energy. They're going to go, they're going to go, they're going to go, they're going to go. They still have 12 joules of energy. 1 unit of charge has that much. They're going to be pushed through here, and they have to spend all of that energy through the speaker. So the potential difference here can only be 10. They have no other place to spend it before they get back to the battery. They cannot move in this direction because other charges are being pushed in this direction and you can't push against them. They have to go back and gain more energy. So they're going to come. They have to spend 10 joules of energy here. So for loop A, we know that delta V1 is equal to delta VA. So the potential difference across the battery, all of that energy is going to be used here. So therefore, delta VA, which is what we're looking for, is same as delta V1. I could have written it that way from the beginning, and that's going to be 12 volts. Box my answer here. I'm going to highlight it. Sorry, I'm using all different colors here. I don't know why I'm doing that, but it's okay. 12 volts, and now I have another piece of information, so I'm going to go ahead and put a check mark here. I found this one, and as soon as I have 2 pieces of information, because now I have delta VA, I can go ahead and find my resistance there. Based on my equations, RA is going to equal to delta VA, or the potential difference across A over current A. You can write this in many different forms, but this is the rearranged formula, and this is going to be 12 divided by the current across A I had found previously to equal to, or sorry, I had the number for, and that's just 6. Sorry, it's 2, and when I divide the 2, I get 6 ohms, and I'm going to highlight my answer or box it, and here we go. another check mark. Our A is found. I'm almost done. I almost have everything. I just need delta VB and RB, and then I need the powers. But the powers, once I have all the information, is going to be very easy to find. So now that I've already dealt with loop A, I only have loop B left. That's the only other information that I can use. So a unit of charge that's passing through the battery, if it doesn't go through loop A, it has to go through loop B. So loop B, I'm going to highlight using let's try using a different color. Let's use green here. So some of those are going to come here, then they're going to go in this loop, and they're going to go all the way back to here. So this I'm going to call loop B. And for loop B, I'm running out of space here. I'm going to write it here, loop B, delta V1, which is the energy that the unit of charge is going to get at this point over here, is going to equal to, they're going to go, 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 go. They're going to use some of their energy here, so that it's going to equal to delta VB plus, and then they're going to go, they're going to go, they're going to go, and they're going to use some of their energy here, delta VC. Delta VC, potential difference across C. So again, unit of charge is going to gain 12 joules of energy here. They're going to go, 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 go. They're going to use some of their energy here, some of them here, and then they're going to go back, gain energy again. They're going to go, they're going to go, they're going to use some here, and that's it. So once I have this piece of information, I'm going to plug all my values in. I know delta V1 is equal to 12. I don't know what delta VB, or potential difference across B, is, but I know potential difference across C. That's given to me, or I found it somewhere. I did find it somewhere. That's where I found it. I found it to be 8. Once I have this, I'm going to subtract both sides by 8. I'll write my math. You don't have to write your math here. I assume that your math is strong enough at this level, and this is going to equal to 4 volts. And I now have my potential difference at this point, and to find RB, I just have to use my equation and divide it by the current, and I get delta VB, which is 4, divided by the current across B, which I have to find is also 4, is going to equal to 1 ohm. And this is my RB. I'm going to highlight my solutions here. I didn't write a therefore statement for this, so let's go back and just put it therefore. If you box it, it's kind of equivalent, like equivalent resistance. It's kind of same or similar to writing a therefore statement. So if you miss the therefore, there's no worries. As long as you box it or underline it or circle it, I'm okay. So here I'm looking for this. I would like you to kind of talk about which loop you use when you're using this information. This is 12 volts. I'm looking for this. I'm looking for some numbers. And that's all you needed to show for that one. Equation, number, number, equation, number, number. Sometimes if you miss some of these, it's okay. Sometimes I mark these out of 2, and you get part marks for showing these. So just try to always show the 3 steps. Now I have all the information I need. I have RB, I have, so all of these things are done. Sometimes I go back and check and make sure that my current is working. So I know that the current across here was I1, which I found to be 6, and since that's split, some of it goes here. So IA I found to be, I'm trying to find all my values here. IA I found to be, oh sorry, I have that value as 2, and the other one is 4, so that makes sense. So the conservation of charge works nicely because the amount that's coming in is equal to the amount that's going out. And we also use the potential differences as well. So we use conservation of energy through these loops. So for loop A, we had 12 joules of energy being kind of electrons gaining that much energy and losing the same amount. And in loop B, they gained 12 joules and they spent about 4 here, and they spent the other 8 over here. So that makes sense as well. Okay, finally, let's do the powers. So I'm going to have to scroll up a little bit, and in order to do this, I need the voltage and the current across them. So I'll just do it over here. I need the power across A, that's the speaker, and that's going to equal to the current across A multiplied by the voltage across A. The current across A was 2. That was given to me in the beginning. Then the potential difference across A was calculated to be 12, equaling to 24 watts. That's power A. I'm going to box my answer, and that's it. Power across B, which is the microphone, and it's not a bad idea to write speaker and mic. This is going to equal to IB multiplied by the potential difference across B. Current across B was given to us as 4. We calculated the potential difference to be 4 as well. That's equal to 16 watts. And I'm going to box my answer. And just to be consistent with everything else I've done, not that I've been consistent with my colors, I'm going to highlight these. All right, and that's it. Really, we're kind of done here. The only thing is, again, for my students who are a little bit more keen into checking their answer, we're going to do the same thing as we did last time. Before that, I'm just going to show you the check marks here. I'm looking for this, this, and this. And yeah, just to check our answers, we're going to check the power and at each component. The power of the battery is going to equal to its current multiplied by the potential difference. Current across the battery was found to be 6. 6 times 12 is going to be 72. You can use your calculator to check. Then I know that the power going through A was 24. We calculated that. We found the power across the mic to be 16. We calculated that. And we just have to check for this power over here, which is current across here times the voltage. The potential difference, or the voltage here for C is, trying to find it, is 8. And the current here is 4, so 4 times 8 is 32. So I'll write it out. And you just want to check to make sure that the amount of power that's being spent on the sources is source is equal to the same as the components or the load. Here, 24 plus 16 gives us 40. 40 plus 32 gives us 72. And that's equal to 72 here. So we can just check and make sure. And that's a great way of checking your answer. Basically, this kind of gives you an idea that everything is correct. At that point, if your answer isn't correct, then you probably have made a boo-boo somewhere. Just go back and check. For example, if your values here are too large, then you can go back and kind of say, oh, okay, maybe some of the values that I found, like the current or the voltage, was too much, or maybe the value here wasn't, either the current or the potential difference here wasn't too much. So you have to go back and kind of use a little bit of your scientific abilities to figure it out. I know this video was long. I hope it was helpful in kind of giving you some idea about how to solve these questions and give you Again, and when you're doing these questions, it's solving a puzzle. Going back again in terms of how you would want to approach these questions is first look to see if you have if any of your components have two pieces of information. If they do, then you can go ahead right away and find the third one, and that's the first clue. Is again, is you're a detective here, and you're just looking for clues. And yeah, once you have two pieces of information, you can find a third one. Once that's done, look for the loops and look how energy is being transferred, how electrons are gaining energy and how they're losing energy, and that will give you information about the potential difference. And if that's not helpful enough, then look at how current is split and look at the different junctions. Just picking one junction is good, and look to see that the current that's coming in to the junction from the battery is the same as the amount of current that's being used from the loads. And that's how you would solve these questions. Again, I hope that it was helpful and have a fantastic day.